Hi guys, Assalamu alaikum. This is Arif. In this video, we are going to see how we can delay a signal or multiple signals using the number of clock cycles. And first, we are going to do that in a system Verilog program and then in a VHDL program. Actually, I have already made a video on this topic earlier, and in that I have shown a few ways to delay the signals using the number of clock cycles, but today I am going to show you some more ways to delay the signals using the number of clock cycles. In the first video I showed you mostly using the after statement of the VHDL and the similar way in the system Verilog program, and now I am going to show you in this video delay of the signal using the wait for statement mostly of the VHDL and the similar way with which we can delay a signal in system Verilog as well. So this is a system Verilog program first, and let me first explain to you. This is a very simple program in which we have defined the inputs like the program counter and the clock and reset, and then there are four signals which are 1-bit output signals which you can see here. And after that, in the always block, which is the main block in Verilog, we have defined an integer int, and we are here converting the bits which we are getting from the program counter into the integer. And after that we have defined a reset, and after that we have defined a if block using the reset signal, and if reset is equal to 1, we are saying that make all the outputs 0. This is the way we are initializing these outputs. And after that we are saying that else, the else block, we are saying that there are 4 type of instructions which are at the different addresses. So from the 0 to 500 address, for example, we have the ALU instructions, R type instructions, and we are saying that if this is the case, implement the ALU logic, and we are saying the all other logics like load, store and branch are going to be 0. And if we are saying that else, if the instruction range is from 504 to 600, then we are saying implement the load logic. And then else, if we are saying if it is from 604 to 700, implement the store logic. And then we are saying that else, if it is a branch instruction, then you can implement the branch logic, and all the other logics are going to be 0. So this is a very simple program, and here we are ending the always block and end of the program and module. So this is our complete program, and you see that right now there are no delays when we are making the logic 1 1 1. So I am going to just show you the output first. Actually, let me show you the test bench as well, so that you guys can understand what we are going to do, what we are going to get. And in test bench also similar, the inputs we are defining as reg, like the way we do in the test bench, and outputs as wire. And here we are calling the main module of our program, and after that we are running a clock here. The clock is 20 nanoseconds, okay, and then we are giving here PC values 11 bits, and we are saying okay, after 100 nanoseconds, actually here the reset is going to be 1, after that reset is going to be 0, and with reset is going to be 0, we are going to implement some logic, right? So this is our end module complete program. Let me show you the behavior so that you guys can understand. Very simple program to implement the delays. Go to the wave window, drag all the signals into the wave window and press run. So this is very simple output. If you guys can see that once the reset is becoming 1 here reset is becoming 1, here it is becoming 0. So once it is 1, no, all the signals are outputs are 0. 1, it is 0 for the ALU instruction. Between 0 to 500, ALU logic is becoming 1 here ALU logic, then load logic, then store logic, and then this one, and then the branch logic is here 1, and then we are saying make all those again zeros because we are applying here the reset signal again. You see here from 0 to 1 it is becoming. So this is just like complete program. Now we are going to see how we can delay these signals from here to here, or from here to here, or from here to here, with the number of clock cycles. So let's end this simulation. Now first thing is that we can delay using this, and this is equivalent to actually the way we delay a signal using the after statement in VHDL. So this is the way we put the time here between this one logic and then the signal, right? And then we are saying comment out these lines, include this line only. Here we are going to comment out this line and only comment in this line, because, and here we are saying actually make the delay after 20 nanoseconds, put here after 40 nanoseconds. Here we are saying this third one delay after 60 nanoseconds, and fourth one we can say is delay after 80 nanoseconds. Just different delays. So this is the first case with which you can give the delays, and let me show you first the behavior. Line 39. Actually this one, I didn't comment out this line properly. So this is the way actually we have given now the delays. You can see, expand this, and we can see the delay first is after the 20 nanoseconds, 1 clock cycle. Second is after this one 40, third is after 60, and the fourth is after 80 nanoseconds. Now we are going to see actually how we can implement this one. And also you guys can see here I am defining here with a star in the always block the sensitivity list. Don't do this because for the most cases these are not going to work. The clock one, the clock option, like in the case of synchronous, and also the asynchronous option, clock and reset, this asynchronous option is going to work in the most cases. And now if we are going to implement this using the number of clock cycles, we can actually come here. Here we have defined time. Here we are going to use this repeat, and it is going to repeat it for one cycle, and then we are going to get an output. Same way, we can comment out this line, and we can include this line. So repeat for 2 clock cycles before giving us one. Store logic 3, and then the fourth one, branch logic 4. So I think all the stuff is complete. Yes. Let's save this. This is actually the after case, which I have already shown in the previous video, but here I am going to show it because we are going to see what is the difference between the after and the wait statement. So you guys can see the same output which we saw earlier. Now go to the next case. And now we are going to see actually if we are going to give the time like this, not in the middle here, like time at the first, then we are actually doing the case which we do using the wait in the VHDL. So this is the way we can implement the same logic in the Verilog. You see where we are giving the time. $60 for the store, and then the $80 for the branch. So now I think everything is complete. Let's run this program. See the output. So you guys can see the difference here in the waveforms already. I mean, once we use the wait statement, how it is delaying actually the signal. I mean, here 1 clock cycle delay, and here it is actually even extending the signal as well by 2 clock cycles. So the period here is bigger. Here it is getting delayed by 2 clock cycles. Here it is getting delayed by until the 3 clock cycles, and here it is getting delayed. Here it is getting delayed by the 4 clock cycles. So this is the difference actually. Signal is getting delayed, but in a different manner. If we are going to put the time before all this, right? Let's go to the first case. Now actually if we are going to delay this signal using the number of clock cycles, we are going to need this line. So I mean, here we were using this repeat before this one, here we are using this repeat before this even. So there is a difference between this line and this line, this one, or this one. Now we can comment out this line and find its equivalent, this line. Now we have to comment out this line and find this line. Comment out this line and find this line. Now I think all the code is complete. Yes, I think all the logic is included. Compile it, run it. So wave window, select all these signals, drop those here. And you guys can see same waveform we are getting using the number of clock cycles. So this is just another way which I wanted to show you in this video. Now we can try to figure out one more way. So actually using this same repeat. Go here. Go here. I mean, this is just a third way with which you can use this repeat in system Verilog to delay something, right? So we have, I think, already included all the lines to our logic. So let's save it. Actually, for this case, we are going to use this one, not this one, because with that one it is not going to behave like the way we want it to behave to delay the signals. So this is actually the output now is different, although the delays are getting the number of cycles delays. Actually expand this. So now you guys can see that actually it is delaying the signal by 1 cycle, but it is also increasing the period as well by this amount of clock cycles. See? And same way this is also increasing the period for which this is 1 as well. It is delaying, and then it is delaying this one as well by 3 clock cycles, and then it is delaying. Actually for the fourth one it is not delaying. You see, just 2 clock cycles delay. So this is just another way to delay your signals, although I am not sure that for what thing it is there, but this is just another way to delay your signals. But everything has a purpose in a language. So I think we have covered now all the cases. Yes, there is one more case which I wanted to show you. Actually, instead of this positive edge clock, we can use this clock simply as well, like this. This is just another way, but the signal would change before the positive edge of the clock cycle. On every clock change, the signal would change. Once we are going to implement using this clock, not this positive edge clock. So like after the half cycle, the signal is going to change, not after the full cycle like the way we saw, but this is just another way. So I think everything pretty much is complete. Now let's go towards the VHDL program and see how we can implement all this stuff in the VHDL as well, which is going to be totally different than the Verilog this time. So let me close these two windows first and let's open these two projects. Let me compile this as well. So where are we? So in the case of VHDL, this is our three libraries, and then we have the project entity, and then we have defined similar inputs, the clock, PC, and reset, and then we have defined the outputs, 4 outputs. And then in the architecture, what we are doing is we have defined here an integer variable, and here we are using the convert integer function to convert the number of bits into the integer. And here actually what we are doing is, since we are going to use the wait statements mostly, so in order to use the wait statements, first of all, the process should not have the sensitivity list. Like in the previous video I have shown you, since I was using the after statement, so using the after, you can have a sensitivity list here like all, process all, like process clock, process reset. But in this case, the sensitivity list we can't use because we are going to use these wait statements mostly. So remember this thing. So instead of using that if clock tick event and clock is equal to 1, or using the rising edge clock, we are going to use this wait until clock is equal to 1, this one. Since we are putting the clock above all the other codes, so it is going to be a synchronous one, but we can use this later after this reset as well, like the way we do in the case of the asynchronous cases. But here the clock is at the top, so the system is going to be synchronous. After that we have defined a reset. So if reset is not equal to 0, or if reset is equal to 1, both are same, we are going to make all these signals 0, initialize all those outputs, and after that we are going to say wait until reset is going to be 0, right? In the other cases we usually say that if reset is equal to 1, else do this, but in this case we are going to write here, after initializing these outputs equal to 0, we are going to say wait until reset is going to be 0, from 1 to 0. And then what we are going to do, we are not going to include any, now the else, we are going to say if, we are going to come straightly to our point instead of using here else writing here. We are going to go to this block due to this statement, as reset is going to be 0. So this is the way actually we can use the sensitivity list, even if we are not using those inside the process statement, but we can sensitize our signal using the sensitivity like this. So in the if block, now we are again saying if the instruction is between 0 to 500 range, that is ALU instruction. So ALU logic implement 1, right? All the other logics are going to be 0. And after that we are going to say if the range is between 500 to 600 load logic, and then we are going to say if range is from 600 04 to 700, store logic is going to be 1, all other logics are going to be 0. And then we are going to say for the branch one, implement the branch logic, all the other logics are we are not going to implement. Then here we are going to end our if block, end process, and end architecture. So this is our complete program. Now a similar way we can see the test bench as well, the test project, and then in the architecture we are calling this main program project as a component. Similar inputs and outputs we have given, and then we are saying defining the signals. These are the clock and reset signals. This is PC signal, and these are our 4 output signals. Here we are using this port map to map all those inputs and outputs. Then in the first process block we are going to define our clock, which is again going to be of 20 nanoseconds, and in the second process statement we are going to give our inputs to our test bench. PC is going to be this value, and then reset is going to be 1, and after that we are going to make reset equal to 0 so that we can implement our logics. So PC values we are going to give, and then we are going to wait, and here we are going to wait after giving all these values, and then we are going to say end process and then end architecture as well. So this is our complete program. Now let me compile and run this program as well so that you guys can see its behavior as well. Similar behavior you are going to see, similar inputs and outputs the way you saw earlier. And now let's go to our this wave window and select all these signals and bring those inside this window and run this program. So this is the way we are going to see our output. Actually, let me see. So yes, without the delays, this is going to be our output. You see, so this is the way actually the wait statement, if we are going to use, I mean we have to define a process without the sensitivity list. So this is the way actually the waveforms are going to show up. But now let's see how the delay signals work in this case. So now let's try to put our first delay, and here I have actually used here transport as well. Transport delay we can use like this, but I am not going to do that. You guys can check at your end. First of all, I am going to show after the using the after statement. So comment out this line, comment out this line, and use the second line after statement. Now comment out this line, use this line after statement. With the transport one also it is going to behave the same way, but for some cases it behaves differently, but for our case it is going to work like the same way. So I think all the lines I have included, right? So now let's save this program. And compile this program. Same way we are giving the delays like after 20 nanoseconds, 40 nanoseconds, 60 nanoseconds, and then the 80 nanoseconds. So you see here 1 clock cycle, 20 nanoseconds, here 2 clock cycles, 40, here 3 clock cycles, and here 4 clock cycles. So here all the outputs are resetting again. But you guys can see how the signal is going to go into the next signals area as well. Same way this is also going. Same way this is also going. But since here we are applying a reset, so after this we are no longer going to see any one logic. So we are getting here the 0 logic only. Now let's end this simulation and try to figure out another way with which we can delay a signal or our 4 signals in this case. So this is actually here, look how I am using 1 star 20 nanoseconds. So here what we are doing, we are saying 2 star 1 star 20 nanoseconds, you see here. And here also I am saying 2 star 20 nanoseconds, and here I am also saying 3 star 20 nanoseconds. So actually in the case of these after statements, the way we are defining here, actually this wait statements, the way we are defining here, the way this thing works is in the case of system Verilog, you guys could see, those were working in parallel, and that's where we were using like 3 repeat by 3 times, repeat by 4 times. But in this case, since the statements go in the series or in a sequence, that's why some delays are going to be already there due to these, like 1 star 3, right, in the ALU. Since these are going after 1 by 1, so that's why I am here using 1 star 2, and it is going to get 2 cycle delay. Same way I am using here 2 star, same way I am using here 2 star 20, not 3 star 20, 3 multiplied by 20, right? So, and same way here, instead of 4 multiplied by 20, I am saying 3 multiplied by 20. Because of the delay, this is actually a very tricky kind of a situation in the case of VHDL. I don't know why this kind of delays are even there, but if you are going to rearrange your test bench, we are going to change this thing here. So this is just like there to model some delays or to show people that this is the way you guys can get the delays. But in reality, these delays are, I can tell you, just like irrelevant to me, but especially in this case, but in some cases they are going to work. But this is the way you guys can give those delays, right? So this is just like you are multiplying your clock cycle. 20 nanoseconds is our clock cycle, right? So we can give the delay or delay our signal according to the number of clock cycles, right? So this is using after. Now I am going to show you using the wait statement. So we are going to include this line. You guys can see now 1 star 20 nanoseconds, and then we are going to delay this signal. This is a separate statement. You guys can see there is a semicolon here. This was a combined statement, so wait statement we can use like this, 2 statements. Actually these are in one line. Same way we guys can come here and skip this line, include this line. So again 2 lines, but again we are multiplying this number of clock cycles. Then we can come here and we can now include this line. And now we can come here and we can include this line. So you guys can see here I am not using here 4*20 like the way, but it is going to get delayed by 4 because of the way we have arrangement in our test bench. And here also 2*20, and here 1*20, and here 1*20 instead of 1*20, 2*20, 3*20, like in the case of the Verilog. There the delays were getting properly handled, but here, I mean, let me show you the output so that you guys can understand it better, because once you guys see the waveforms, then through the observation the things are easy to understand rather than through the talking. So let us wait for our waveform window, and now I am going to drag all these signals inside our waveform window, and let's run this program. And now if you guys can see, you can see here 1 cycle delay, 2 cycles delay, 3 cycles delay, and then 4 cycles delay. But you guys can see that signals are coming to the second window as well. Like once the instruction is no longer this one, the ALU1, here it is also becoming 1 for some time. Here it is even going into the area where the reset is already 1. So this is the way actually the wait statements behave. So very weird way, but for our case probably they are behaving like this, but for some other cases I think they have a purpose. But this is the way actually we can implement these things. Now actually, instead of using this multiplication, this star, we can use the clock cycles as well. And in order to do that, we are going to run a loop. So in order to run a loop, there are actually 2 ways. So I am going to skip these lines actually. Let's start from the beginning and skip this line first and include this line, and then we have to include this second line as well. And here we are saying that using this loop, I mean run this loop from 1 to 1 only 1 cycle, and here at the rising clock edge we are going to say end this loop, and then we are going to get wait until rising clock edge, right? It is just like positive edge clock, the way we were using in the Verilog program. And here we are going to get after this logic is going to be 1 after the delayed, and then we are going to say exclude this line, include this line, and include this line as well. So these 2 statements we are going to use, and here we have to include this line and include this line, and same way we are going to exclude this line and include this line and this line. So here you guys are also going to see that, I mean, even in these loops they are not running parallel. So I mean they are going to be in the series, so some cycles delay we are going to already get. That's why I am saying here from 1 to 1 clock cycle, and then I am saying from 1 to 1 for 1 clock cycle, but it is going to get 2 cycles delay. And here I am saying from 1 to 3 from for the branch only. I don't know why even this thing behaves like this, but for the 4th we have to run these 3 clock cycles, and now you guys are going to see the output. I mean the way the delays are there in the case of system Verilog, they look very proper, and you guys can delay a signal the way you want. But in the case of delays of the VHDL, I have seen that you have to use the counters or whatever in order to give your signals delays, because these delays are never going to work. I mean, the way they behave. I mean, you can see 1 cycle delay, 2 cycle delay, 3 cycles delay, 4 cycles delay. But the way you guys have seen, I mean, I was not giving the number of cycles the way they should be given. I mean, even after second signal, 1 clock cycle, because there was a clock cycle previously already spent, so we were going to get 2 cycle delays. But delays, if you guys are going to give like this, that is going to be total confusion in your code. So after this line is also same. So here we are just saying that until clock is equal to 1, so until rising edge clock or clock is equal to 1 is just like same, or clock is equal to 0, and until falling edge clock, those two are also same. So I am not going to include this line. And actually I am going to show you now the next case. So exclude this line and come to this line. Now you can see that here I am putting here this signal inside this loop. Previously they were outside this one. You see this line we were including, but here we are including just this line because we are putting here logic is equal to 1 inside this loop. Let's start from, I mean, top actually, and exclude these two lines first and include this line, because this time we are going to do this ALU logic equal to 1 inside this loop, you see, and loop here. So we are not going to use any second statement, and come here and include this only line, because we are going to make this signal inside our loop 1. So here also. Now let's go and run this program first, so that we can see the output and understand what is going on here. I think I have not included this line, right? This line we had to include. Yes, this is also included. This is also included, and this is yes, now it is complete. So today you guys have seen actually one extra thing, that how we can sensitize our process statement even if we don't use the sensitivity list in the case of wait statement in the process, but within the code we can sensitize this. So you can see that 1 clock cycle delay, 2 clock cycles delay, 3 clock cycles delay, right? And here you guys can see we saw even in the case of system Verilog as well, this fourth one was getting just 2 cycles delay. So here it is also showing some weird behavior. So this is odd behavior. This was the case which we saw in one case once we were doing the system Verilog as well, if you remember. So first 3 signals were getting the same number of clock cycles which we wanted to give, or the delay which we wanted to get, but Now let's start from here top and go, and we see that this loop we are running from 1 to 1 only one cycle, right? And then we are saying that this loop also we are running 1 to 1, but we were going to get 2 cycles for the second load one, because one loop already has been done. So this is the way actually the delays in this work, like in the case of the system Verilog, they work more properly. And you see here I was again giving this 1 cycle delay, but in the waveform we saw the signal was getting delayed for 3 clock cycles, right? And same way in the case of 4th clock cycle, we are giving here like running here this loop for like 1 clock cycle only. But even if we make here like 1 to 5 for 5 clock cycles, you guys are going to see the same output. Signal is going to only go up to the 2 clock cycles. So this is the way actually in a weird manner these delays are there. And now I am going to show you one last case for this VHDL as well, and that is actually using this for loop. And in this for loop actually we are, first let me skip out these lines and include these lines, and skip out these lines and include these lines as well. So now I think the code is complete, but what we are doing here is like we are, even before waiting this clock cycle, we are putting here this load logic is equal to 1. Like in the previous case it was here. Now in this case it is actually here, right? So now what it is going to do, it is going to give us some delay like in the previous cases, or what it is going to do. And for this case actually I have to give it this asynchronous clock as well. And now I think all the code is complete. But you guys can see, here even I am running here 1 loop for once, loop for once, loop for once, and loop for once. But let's see what happens. Let's simulate this. And run this. Now here you guys can see that signals are not getting, actually these signals are getting delayed, but the way how they are getting like 1 cycle delay, 2 cycle delay, 1 cycle delay, and then the 2 cycle delay. And you guys can see how the waveforms are behaving. The signal is going here, getting extended. Signal is getting here, getting extended as well. By 1 clock cycle, and then by 1 clock cycle here. So this is the way actually we can extend our signals as well. That's what I wanted to show you using the for loop. And now I am going to show you what happens if we are using here the synchronous clock. So include this line and exclude this lengthy asynchronous clock. So let's synchronize our circuit. So now let's drag our signals inside this window and then run this. Now you see here, the signal is getting extended. The signal is getting extended here. Instead of getting delays, we are getting this signal extended. So this is just like another thing which I wanted to show you. I mean, the way the loops or the repeat statement in the case of system Verilog, how they run and then they give you the delays. I hope you guys have enjoyed this video. Have fun.